Hello everyone and welcome to this video in which I'm going to introduce my latest project. I've been doing quite some radio repair in the past, and while doing so I realized that having a spectrum analyzer would be hugely beneficial. However, unfortunately I don't have a spectrum analyzer at home, so I started to look for products that might satisfy my need. And while doing so, I came across a website from a guy called Scotty, on which he essentially describes how he built his own 0 to 3 GHz spectrum analyzer. At first, I thought that such a project was way over my head, because I've done some RF work before, but I'm not an RF engineer, so clearly I never built anything on the scale of a spectrum analyzer. But when I started to look more closely, I found quite a number of reasons that enable me to do this nonetheless. So I decided to build a spectrum analyzer based on Scotty's design. My motivation for doing this is actually quite manifold. First of all, of course I wish to have a spectrum analyzer, so I could either buy one or build one. But building one has quite a number of interesting advantages. First of all, this is a very cool and fun project to apply and gain some more RF know-how. Second, and this is quite important, Scotty's spectrum analyzer is actually quite modular, so there is sort of separate PCBs for all the building blocks of the spectrum analyzer. For example, this is a lock detector, an ADC, and essentially that allows me to iterate over each of the building blocks separately before I put everything together. Then, of course, this project allows me to show a lot of interesting stuff on my video blog, so you can expect actually some sort of project log for all the steps of this project. I will make a video in which I explain the circuits and show my PCB and outline my design decisions and discuss some theory. And the last reason, I'm not really sure about that, but it might be cheaper to build your own. However, if you do it the way I do, I'm expecting to go over several iterations of some PCBs, and in the end that might eat up whatever the difference is between your own spectrum analyzer and one that you buy. But anyway, I'm hoping that this is going to be a really cool and interesting project in any case. Scotty's PCB designs are available on his website, but I decided to go for my own PCB design for two reasons. First, if I'm rolling my own PCBs, I have to spend a lot more attention to the design, and I'm forced to understand the meaning of the parts in much more detail. And I'm actually interested in that, so that's reason number one. Reason number two is his designs are designed in a software called, I'm not really sure actually, it's either PCB Express or Express PCB, and apart from problems I have because the software doesn't run on my operating system, the software is sort of tied to a particular PCB manufacturer, and I don't really like that. And one of the goals I have with this is to actually change a few aspects, especially later in the design process. And if I have to fiddle around with this PCB Express thing, I think that will hinder me. So I'm doing everything in KiCad, and actually my designs are available on the file section on that Yahoo project site if you're interested. This is all open source hardware, and Scotty actually encouraged me to keep it that way. So this design is freely available, and if anyone is interested, you can just go to that file section and look at it. I'm about to give you a high-level overview of Scotty's spectrum analyzer in a second, but before I do that, I want to make sure that everybody understands the concept of a mixer. Now, if this popped into your mind when I said mixer, I will make sure to have a bunch of videos in the link section of this video that explain in quite some detail what mixers are and how you use them. I don't think it makes any sense to explain this now and here, because quite a bunch of people have done an excellent job in doing so. So in a nutshell, an RF mixer has two inputs, an RF input and a local oscillator input, and one intermediate frequency output. And all the mixer does is it multiplies these two inputs here together, and what you then get at the IF output, the intermediate frequency, is the sum and the difference of the two input frequencies. There is much more to mixers than just that, but as I said, if you're interested in that, just pause this video now and have a look at the links that I put in down below. This is the block diagram of the spectrum analyzer I'm about to build. And this is also the block diagram of Scotty's spectrum analyzer, because there is not much of a difference yet. So I want to emphasize yet again that Scotty deserves all the credit for this, and I'm just explaining what is going on. The blue arrows are the signal path of the input signal as it travels through various blocks of the spectrum analyzer. So we start here at the input, and then this goes all the way down to an ADC at which some voltage is then digitized. By the way, this is meant to be operated from a computer, although I don't think it would be that difficult to put in some embedded computing platform to have this as a standalone device. There is two things to note before I start with a walkthrough. First, there is a master oscillator up here running at 64 MHz that is used to derive all the timing and the frequencies that are used inside the spectrum analyzer. Second, this is a sweeping type spectrum analyzer, which means that there is a voltage control oscillator in here that actually sweeps from some starting frequency to some end frequency during the measurement. So let's say, for example, we're looking at a frequency range of interest between 0 and 20 MHz on the spectrum analyzer. This VCO actually sweeps from 1013.3 MHz to 1033.3 MHz. And the numbers I put in here relate to the one point in time at which we're just measuring the input power at 10 MHz. So let us start, and let us assume that we're applying an input signal to the spectrum analyzer that has frequency components of 10 MHz and 20 MHz. Because we're sweeping at 10 MHz right now, we're expecting to measure these 10 MHz here, but we should ignore the 20 MHz that are also applied to the input. Both the 10 and the 20 MHz at the input are mixed with 1023.3 MHz. And this will essentially give 4 frequency components at the output, because the 10 MHz will lead to an addition and a subtraction from 1023.3 MHz, and the same will happen to the 20 MHz. So in the end, we get 2 frequency components that relate to the 10 MHz and 2 frequency components that relate to the 20 MHz. For sure, we want to filter out the frequency components that relate to the 20 MHz, and we also want to filter out one of the 2 frequencies that relate to the 10 MHz. And this is what this bandpass filter here does. And actually that is going to be quite an interesting one, because this is not one of your regular filters. This is going to be a sort of a microwave cavity filter thing that I haven't really decided on what exactly I will do here. But in the end, this bandpass filter will filter out anything except 1013.3 MHz. And that is one of the 2 frequency components that originate from the 10 MHz. So we will get rid of these 2 guys and also of this guy here, and just have 1013.3 MHz at the output. This will then get mixed by 1024 MHz, and this will give again 2 frequency components, the sum and the subtractions of the two input frequencies. And this happens to be 10.7 MHz as well as 2037.3 MHz. In the next stage, we're filtering out the 2037.3 MHz, so we just get the 10.7 MHz at the output of this low-pass filter here. And this is also an interesting filter which we'll look in detail at. The 10.7 megahertz then get amplified by this IF amplifier, but they're just being amplified, so that's 10.7 megahertz again, that are filtered by a 10.7 megahertz bandpass filter, and these are then fed into a lock detector, which outputs a voltage that is proportional to the log of the input power. And in the end, we just have an ADC that measures that voltage and sends it off to the controlling computer. So in essence, that's how this spectrum analyzer works. But you might have noticed that there is quite a few things that you could also do otherwise, and we'll have plenty of opportunity to discuss why it's done that way in particular, as opposed to any other way. For example, why is this 10.7 megahertz here? Would this also work with some other frequency? Is there a particular reason why this is 10.7 megahertz and not anything else? Why are there two stages of a mixer and not just one? Would this also work with just one stage, or is there an advantage in actually having this two-stage topology here? Then why is the output of the low pass first amplified and then fed into a band pass? Would it also work if you would swap these two and first filter the output and then amplify it? And also, this low pass outputs nothing but 10.7 megahertz. Which is then amplified, but still 10.7 megahertz. Is it really just that, or are there other frequency components? Why do we have to filter out the 10.7 megahertz here? Because in the end, starting from here, everything seems to be 10.7 megahertz. So, as you can see, there is lots of interesting questions that are, in my opinion, worth discussing, and we'll for sure do that in future videos. Finally, let me talk a little bit about the work I've done so far in this project. The blocks in the block diagram that had a green dot in the top left corner are the PCBs that I have already designed and got them back from manufacturer. That's 5 boards, and I laid these out on a 20 centimeter by 5 centimeter panel and had them manufactured by Seed Studio. I ordered 5 panels for a total of about $50, which is quite cheap for these PCBs. That's the boards you can see here. That's just the front and the back side, and I'm very happy with the quality, especially with the kind of RF via stitching fences that I have around the critical sections. One interesting thing to note here is that on their website, Seed Studio tells you that you're not supposed to put more than 4 PCBs on your panel. And of course, I have 5. This, by the way, is the PC control board. That was not part of the block diagram, but it just contains some power conditioning stuff, a 20 volts DC to DC converter, as well as some latches for computer operation. So there is that one, then the ADC, the lock detector, the 10.7 megahertz frequency synthesizer, as well as the RF mixer. I didn't want to put sort of routed cuts here because when I read that I was supposed to not put more than 4 PCBs on my panel, I just decided to try it and to put 5 on there, and nobody complained, and I just got back the boards without any notice. So I didn't want to make it even more obvious that this was sort of panelized. So I didn't put sort of a routed cut here, and also Seed Studio doesn't do V-grooving, which leaves me with a pretty cheap panel. But I had to cut them apart myself. And originally I wanted to use the Bashli, which is sort of a local university electronics club. They have this nice and powerful table saw for cutting PCBs, and I wanted to use that one, but unfortunately that was out of service. So instead they gave me sort of a hacksaw, and I had to cut it manually, and you can see in the result there is like this very crappy non-straight edge here, but in the end, I mean, that's not going to take any role in whether this works or not. And for now, I just couldn't wait any longer for the table saw to get fixed, so I decided to cut it by hand. Anyway, The mixer board, on the other hand, is unfortunately a bit of a fail. The reason for that is, after I had designed the first 4 boards, I realized there was still a bit of space left on the panel, and I looked at the mixer design and realized that this design was quite easy to do, so I just whacked it onto that last part, but I essentially messed up 2 things while doing so. First of all, so that's the mixer board here. The first problem is that I really should have pulled back the solder mask from the transmission lines, and every RF textbook will tell you that you really should do that for transmission lines in these frequency ranges, out of 2 reasons mostly. First, the solder mask will slightly change the dielectric constant of the FR4, and if this is a tightly impedance matched transmission line, you're going to mess up your match. Although I'm not too concerned about that. And the second reason is that there might be a bit of leakage on the solder mask, and that's another reason to remove it, such as I did here, where the impedance matching transformer is supposed to be soldered on. And the second and probably larger problem is that if I turn around the board, the RF input and the IF input are very close together. I'm not sure what I was thinking when I did that, and it only occurred to me when I actually looked at the board after I got them back from the manufacturer. So I'm really not too confident about that. Although this would be an interesting experience to actually build it up and see whether there is any issues with isolation between these 2 ports. But what I will do, because this is another really nice thing about this project, there is quite an active builder community, and at least so far, they have really been nice to me and answered all the questions I asked. So I'll just send them a picture of that and ask whether this might be too close, because these guys have a lot of experience. And just in case they're watching the video, I have no idea how large that distance is in imperial units. So I just hold on the caliper, and hopefully you can read on. I believe this is the inch scale here, and or is it? Yeah, it is. So that's, I think, 1 inch, and the distance is sort of a little bit less than half than that. Just for reference, I actually never understood these scales. But anyway, that's it for the PCBs. Another interesting thing to note are these SMA connectors, because this whole design is so modular that you have connect everything through SMA connectors. Now, one advantage of that is that for example, if I mess up the mixer, I could just go and redesign the mixer board alone, and I don't have to respin the whole board with everything else on it. But the disadvantage is that you need quite a number of these SMA connectors. And it turns out that if you're ordering these from, let's say, from Molex in low quantities, at least these are fairly expensive. So I thought about getting some of these low-price SMA connectors from a manufacturer from China, and I was a bit concerned about the quality of these. I was particularly concerned about things like insertion losses, and I asked on the mailing list of the project whether it would be fine to use these, and Scotty replied and said there was no problem. So I went off and ordered 50 of these SMA connectors from a Chinese manufacturer from eBay. And I was looking around on eBay and found a decent manufacturer, although I noticed that they had sort of a technical drawing on the website, and the measurements were sort of different from what you'd expect from a standard SMA footprint. So I designed all the boards with these sort of special dimensions, but then I noticed that there was something else that was completely inconsistent on the technical drawing. So I sent off an email to the eBay seller and asked about the proper dimensions, and I actually got back a few pictures of somebody holding the SMA connector in his hand with a caliper, showing me the dimensions, and that was actually that was quite helpful, because then I could actually get a picture of the SMA connector and at least assess the quality a little bit. And it turned out that the measurements on the technical drawing were wrong, and it also turned out that these fit perfectly fine on a standard SMA footprint. So I changed all the footprints yet again, but luckily I was able to catch that problem, because otherwise I would have ordered all of the boards with SMA footprints that wouldn't fit. And while I'm at that, these are actually female SMA connectors. That might be a bit weird, because there is an outside thread here, but there is a hole. That's why these are female, for obvious reason. But some people get confused about that, because they see sort of this outside thread, and because a typical connector has an outside thread and a pin inside, they get misled and think that this is a male connector, but it's not. This is female because it's got a hole. And if I actually manage to find a male SMA connector somewhere, give me just a second. Here is one. I'm not sure whether you can see that on camera, but there is actually an inside thread but a pin inside, and that's why this is a male connector. So this is something that you should be aware of in case you want to use SMA connectors. And lastly, I ordered quite a bunch of parts from DigiKey for like the ordinary stuff on here, as well as there is a few special RF components that you need, such as mixers and VCOs and stuff like that. And it turns out that Mini Circuits has a kit that they sell at about $100 that has all the parts that are specifically necessary for this spectrum analyzer. And I contacted Mini Circuits and asked for that kit, and they sent me off just the kit. And that's really nice of them, because otherwise these parts, if you were to order them separately, would be much more expensive. So I asked them about that kit, and that was no problem at all. They just sent me this kit for $100 plus like $20 shipping fees or something, and that's impedance matching transformer, mixers, buffers, VCOs, and stuff like that. So I got that as well. And the next few steps are, first I have to get a PC with a parallel port, because it turns out that the control board is meant to be controlled by a PC with a parallel port, and I just don't have any of these PCs, so I'll try to get one of these. Although I will redesign this board, because I don't really like that, but I thought for starting I should really start with something that is very close to Scotty's spectrum analyzer, not to run into troubles there. And I will install Windows on that PC, because the original software is Windows software for the spectrum analyzer, although they're currently rewriting this in Python. So I will just start testing with the Windows software, and then switch to the Python code as it matures, and I'll probably also be able to contribute a little bit to that code. And then I will start building. I will start with the control board, and that will be actually the next video in this series, where I build everything up and discuss the circuitry and make some testing, some measurements, yeah, that's basically it. So I hope you really found that introduction interesting. If you have anything to share, to comment, please do so down below. And otherwise, I thank you for watching, and see you next time.